Checking 1 2 3. Checking. All right. Before we start, do you have any question from Monday? Right. As always, if you have any question, please put on the chat, and I will type the address that you can send email during the stream. Right. So we start today. Right. So we continue section 7.5. Right. When we go to section 8.4, we will prove this one, this theorem easily. But for now, I'm just going to write out. Right. We don't even need to memorize these formulas because we can prove it later. And sometimes deriving from scratch is easier than try to memorize the formula. On the note, I forgot to put the dx there, sorry. Obviously, I do not memorize any of this because whenever we need it, we can prove it. It's not worth memorizing. So we're going to do this one. And of course, obviously, we have a constant square minus x squared. So this is going to be the sine inverse. So we're going to use that. First, as a 4, we can always take that outside. I'll just have 1. Square root of 25, we can write that as 5 squared. So we have to have the formula that look exactly like, have the integral look exactly like the integral. Here, obviously, a is going to be 5. So we're going to have sine inverse. Of course, there's a 4 in front of that. So that gives us the 4 times sine inverse. And then x over a, x over a is 5. Right, so just like that. Of course, plus a constant c. Right, so that's it. 2. We have dx over 9x squared plus 4. Right. So first, usually when we have the integral with the dx here, I'll try to move dx back to the end of the integral. Right, like that. Now we're trying to look for the form of the integral. Obviously, this one doesn't have a square root in it, so it has to be this one, right? So on this one we only have the x squared by itself. So in here we have to get rid of the 9 here, so we have x squared by itself. So I will rewrite this. Now to get rid of this 9 multiplied to x, we have to divide by 9, meaning that multiply by 1 over 9. Right? And I will just multiply it in. One over 9. 1 over 9 times 9. The 9 and the 9 cancel out. We have x squared. The 4 times 1 over 9 is 4 over 9. And then we have dx. Sorry. Right. Now, we'll move the 1 over 9, the constant, on the outside. And inside we have x squared. This is a squared plus x squared or x squared plus a squared, doesn't matter. What matters is we need a square. So we're going to write 2 over 3 square. So that is 4 over 9 and dx. And the integral said it's going to be 1 over a tangent inverse of x over a. So 1 over a is 2/3. So we divide by 2/3. And then tangent inverse of x over a, also 2/3. Right, and then finally divide by fraction is multiply reciprocal. We have 3/2. Tangent inverse, also divide by fraction, multiply reciprocal, 3/2 x plus c. Right. So that's what we have for section 7.5. Now we go to 7.6. Right. The L'Hopital rule and Lagrange function. By the way, if we cannot type the head, we're going to write the s here instead, just like what we have on the note. right? First, L'Hopital rule. Right. So before we go to that, to the theorem, what we have just write with review. Here are some indeterminate form. Right. We have 0 over 0 is indeterminate. This is from car 1. Infinity over infinity. Oh. Infinity minus infinity. And then there will be some other forms. Right. So in this section, what we have the form for the new form of indeterminate is going to be in that form. So when we have what new in this section is also 1 to infinity, 0 to the 0 power, or infinity to the 0 power. Now we take care of this new indeterminate forms. Right. A common theme here is that they all have powers. So every time we have powers, if we check the LN on both sides, and that will be easy. So first of all, we let L. Okay. Procedure of finding so every time we have a power, first we're going to take the L equal to where we take Ln on both sides pretty much. For example, let's say we have y equal to the limit when x equal to a, something like that, right? And now if we take Ln on both sides, I can just put the Ln right here in front of f of x. So I have Ln of y equal to limit x to the a, and then we can take since there's Ln there, we can take the exponent outside. So we're going to have g of x times Ln of f of x, and that's what we let equal to L. So we take Ln here and take the g of x outside. So we have g of x Ln of f of x, right? As I said, this can be put in these forms, and this has to be indeterminate. 0 over 0 or infinity over infinity. So not only we put it in this form, we have to turn that into a fraction as well. So we certainly will do that. And then finally, at the end, we just raise both sides to exponent. If we have ln of y raised to power of e on both sides, and that cancels out, we get back to y, right? So finally, the limit as x goes to a of f of x to the g of x will be equal to e to the L power. Right. So first, we take ln on both sides, bring the exponent down, and make that equal to L, and change that to a fraction because it has to be in indeterminate forms of these two forms. And then whatever we find using the Hospital rules, raise both sides to the e power. That get back to the limit of the function. Alright, let's see how it works. Example. Find the following limit. First we have limit of x to the 0 power. 0 from the right hand side of x to the x power. Right. So a little bit review here. We have anything to the 0 power. I should not use that. Let's say anything raised to 0 power is 1. That of course when x not equal to 0. Now, if we have 0 raised to any power, that is going to be 0. Of course, x is not equal to 0 also. So those two are easy, right? The question is, what is 0 to the 0 power? If we try to put that on the calculator, 0 raised to the 0 power, as I said, it doesn't work. Simply because it is indeterminate. Alright, so first of all, this is in the 0 to the 0 power determinant, indeterminate form. Right. Now we do it. First, let's say if we have y equal to the limit at x go to 0 from the right hand side of x to the x. First we'll take the ln on both sides. So actually I should write it here. So first we let y equal to the limit I will leave a space here, x to x, like that, right? Now we can check the ln on both sides, and we'll make that equal to L. Right. When we take the ln on both sides, we can bring the exponent down. I'm going to put that there. And that is the product. Right. So good. Take ln on both sides, make that equal to L. Right. Next, what we do is have to somehow turn into this indeterminate forms. So that is a fraction. So we have to bring something down to the denominator, and that should be easy. the ln of x cannot do anything with it. But the x here, by default, to the first power, so we can write the bottom, x to the negative 1 power. Right. Now we do have fraction. Right. Then we can use the L'Hopital rule. This is in calculus 1, the L'Hopital rule, meaning that if it is in the indeterminate form of the rational function, we're going to take derivative of the top divided by derivative of the bottom. Derivative of the top divided by derivative of the bottom. And by the way, that is not the quotient rule. It is the L'Hopital rule. So what we do is we're going to take derivative. Just wanna. That is the L'Hopital rule. Take derivative of the top divided by derivative at the bottom. Right. So that is the L'Hopital rule. Derivative of ln of x. By the way, I hope you organize and keep the note for every day. This is the first thing we write yesterday on the derivative and on the integrals. Right. So that's from the first day. Right. Derivative of ln of x is 1 over x. And derivative of x to negative 1 is negative x to the negative 2. Right? Now, x to negative 2, if we move to the top, it becomes x squared, right? So there's nothing at the bottom. First of all, there's a minus. We have 1 over x on the top, and then move x to negative 2 on the top. Become x squared, and there's no x at the bottom. Right? And then x squared, or I just write negative x squared over x, or just negative x. And when x go to 0 from the right hand side, it doesn't really, if it is the right hand side or the left hand side, put in 0 here, we have that equal to 0. Right, so when we have ln, L equal to ln of y is equal to 0. So I'll get back to that, and we write L equal to ln of y is equal to 0. Now, we took ln on both sides earlier. Now to undo it, we'll raise both sides to the power of e. And e to the 0 power is 1, and e and ln cancel out. So we have y equal to e to the 0 power, which is 1. And y is the limit of the original. So we have limit as x go to 0 from the right hand side of x to the x equal to 1. Right. I write a little more step done. Oh, sorry, I didn't read that earlier. The x to negative 1 here is because of this x. By default, x to the first power, and we bring that to the bottom, become x to negative 1. When we bring to the denominator, we change the sign of the exponent. Sorry, I didn't see that question, but that's what it comes from. And then after that, take derivative of the top, derivative of the bottom, That is the Hospital rule, and simplify, and we have that. Finally, raise both sides to the e power. E of ln of anything. E and ln cancel out. So in this case, we have just y. On the note, we have the picture, we have the graph. This is the function of x to the x power. When x goes to 0 from the right hand side, it goes to 1. So that's why we confirm it. Right. Once again, the x to the first power, we move that to the bottom. Next example. This is the classic one. Kind of similar to what we have here. Oh. Two. What is the limit as x go to infinity of 1 plus 1 over x to the x power? It's always there's something with the powers in this section. Right. So first, we're going to let y equal to that. And we're going to take the ln on both sides. When we take the ln on both sides, we're going to put the ln right after the limit. So we'll take ln on both sides. And make that equal to L. Right? And then with that, we can take the exponent outside. By the way, I should write that formula down as well. So ln something with the power, we can always take the power outside. And that's the reason we take ln on both sides, turn the power into the product, and from the product we turn to the quotient. Once again, we have x to the first power. Bring that to the bottom, become x to negative 1. So the idea is, once again, powers, when we take ln, that turn into a product, bring something down to the bottom, turn into a quotient. Ultimately, we need something in this indeterminate forms. By the way, talking about indeterminate forms, this one, when x go to infinity, 1 over infinity is 0. So we have, in this case, is 1, 2, infinity indeterminate. Right. Of course, if it has to be indeterminate for us to do that. If it is something that's rather clear, then we just go ahead and find the limit without doing any of this. Right. Right. Now, just like last one, we have the x here. Move that to the bottom. X to the first power, move to the bottom, becomes x to the -1. The top we still have ln of 1. But let's just write x to the -1 because that's also 1 over x. We write that as x to -1. Because we're going to take derivative, it is better to put as a power, so we can use power rule. So 1 over x, x to -1, x to first power, bring to the bottom, become x to -1. Oh, this one, the x to the first power originally, right? When we move that, and the power will stay there, yes. But as a product. And so, that is the product. If we move x to the first power down, it becomes x to -1. Yeah. And 1 over x, if we move the x to the top, it becomes x to -1. And there's nothing at the bottom. Yeah, so we just take the power down as a product turn into a quotient. But we have to change the power to negative. The opposite, that is. Right? Now, we have a ratio of two functions. That's where we use the Hospital rule. Take derivative of the top and derivative of the bottom. Yeah. So this one, move it outside, turn into a product. Right. Take derivative of the top and derivative of the bottom. Right. It will be easy. Derivative of the bottom, x to -1 is -1. Original power -1. -1 is -2. So that is derivative of the bottom. That part easy. Derivative on the top, it has the ln. So it's going to be the reciprocal function. Have a bunch of different colors here. So here we have ln of something. It's going to be 1 over the same thing, and we'll take the derivative of that. So that is the chain rule, and inside the parentheses 1 plus x to -1. Sorry, kind of small there. Right, now we have 1 and 1 plus x to -1. We cannot really do anything with it. derivative of 1 plus x to negative 1. Derivative of 1, that constant will be 0. Derivative of x to negative 1, take down the power, so it's negative. Oops, I forgot the negative, did I? So it's going to be negative x and to negative 2. Right? The power rule, negative x to the negative 1 minus 1, that makes it negative 2. Right. Cancel the whole thing. So now we have just that. Right. Now, before we go any further, if we have to use the Harper rule or not, just put in the numbers and see what we have. Now, if we have 1, sorry. Before we do that, let's just rewrite as one more steps. X to negative 1, we can write as 1 over x. Right. Now, let's put in infinity. 1 plus infinity. Right. So what is 1 over infinity? We have a finite number divided by something that indefinitely big. So we start with a small number, a constant, and we divide by a very big number. The bigger the number we divide by, the smaller we get. So ultimately 1 over infinity, that one goes to 0. So this equal to 1 over 1 plus 0 or just 1. Right. So L equal to Ln of y and equal to 1. And now to get rid of the Ln, we'll raise both sides to the e power. E and Ln cancel out. So we have y equal to e to the first power, which is e. Which means limit of x goes to infinity of 1 plus 1 over x to x power equal to e. And this is a classic problem. This is the definition of the natural base e. And if we graph that, you see it go to about 2.71828. Yeah. So approximately 2.718281828. Right, so that is that. Right. Next, we have the ranking growth rates. Just a second. Yeah, just weird in this section we only have one subsection. It's kind of weird. Right. As x goes to infinity. Actually, this will be very important in chapter 10, I think. So now what we try to focus here is to see which one of those functions go to infinity faster. That's the ultimate goal, right? So we have a linear function m to the x m to the x power where the base is positive. Next we have polynomial or just power function. X raised to a constant power. Next we have x to the x, or the super exponential function, or just a tower function. It is tower because it goes to infinity very fast, almost vertically. And then the log. And then we have other function, the ln q of x. That is q, not 9. Right? By the way, that is the 9 here. What it actually is, we take the ln of x first, and we'll raise that to the q power. That is q, not 9. And the q is positive. And then next we have the power of polynomial times the ln of x. And then 7. We have the exponential function. The goal is which one goes to infinity faster to find. So when we list all those functions, the theorem is this. Suppose the function where both go to infinity. Both of them go to infinity when x go to infinity. Then let's just say f of x is faster. Than g of x as x go to infinity. If so, if go faster, then we have the following. We just take the ratio. Now, sorry, this is opposite to what we have in the note. So to be consistent, let's write the note. if if f of x at the bottom, no, that is not 9, that is q. Yeah. Yeah, so that's not the 9 power, that is the q. Yeah, we should use something else that other than q. But right now, we have the ratio of two functions. Think about this. F of x go faster to infinity. Now, if it go faster to infinity, meaning that f of x is bigger. So if we have a ratio, the bottom go to infinity extremely fast, the top not so much. So what we have is, on the top, it's a lot smaller than the bottom. So in that case, it is equal to 0. Because if the bottom is too big, the top is too small, the ratio is very small and essentially goes to 0. That would be the same as if we flip it. If we flip it, the top is f of x is extremely big, the bottom is too small. Too small, it doesn't matter. Like if we have $10,000 divided by 2, it's not as much. But if we have infinity divided by 2, of course that's still infinity. No, I don't get your question. Alright, you mean this number 5? Oh, that's the Roman numeral lowercase. So that's instead of capital V, that's the 5. And all of this are Q. Yeah, capital Q. But I write lowercase. It's much easier to type that than over there, that to the Q power. Yeah. Right. Now, once again, if the top is too big, like infinity, the bottom is small, it doesn't matter. It will be infinity. Now, I still have one more. F of x and g of x are comparable rate. If the ratio is a finite number. I should write this on the next page, sorry. Right, so when we check the ratio, if it is equal to infinity, the top is too big, the top goes faster. If it is equal to 0, the bottom is too small, the bottom, sorry, let's say that again. Let's say if we have a fraction, if this is too big, then the top has to be infinity. If we have the ratio that is equal to 0, the bottom has to be very big. So infinity is the bottom. So the bottom go faster. Right? We'll get back to this with the few examples. Right. I don't know why this section only have one subsection. Right. Now we compare. That is example. Sorry. I have to be organized here. Example. We just compare the rate, the gray approach. So which one go faster to infinity? Right, the first example, we have two functions, ln of x, and the second function, x to the p power. So the natural log and the polynomial or the power function. Right. So by the definition, we just take the ratio of them. Doesn't matter which one over which. I will take the ratio. By the way, both of this function, when x go to infinity, they both go to infinity. If we have one function, for example, if we have the sine function and then e to the x, the sine function just go between -1 and 1. Suddenly e to the x will go a lot faster to infinity, right? So that one does not go to infinity. Only this one does. So e to the x go to infinity a lot faster. So we have to kind of think about that. Right, now we just take 1 divided by the others. How about take f of x divided by g of x? It's very easy. Just take the ratio. Now, so we take the ratio, and now we just find the limits. This one, as mentioned before, if we're going to put in the numbers infinity, we have ln of infinity or infinity to the p power, where p is positive. This we have infinity over infinity indeterminate form. That means we have to use L'Hopital rule, right? Apply L'Hopital rule. The L'Hopital rule means take the derivative of the top, divide by the derivative of the bottom. And that is not the quotient rule. Right. Derivative of ln of x, that is 1 over x. Right, just one more thing I haven't mentioned. All the tests will be on my MATLAB, pretty much at home. So it suffices to say that if I ask you to put all your note away, it's kind of unreasonable. So all of the tests is you allowed to use the formula chart. Something like this will be helpful. What we have on the first class, or I will send you the formula chart. Something is easy to reference. Right, derivative of x, 1 over x, derivative of x to the p, that is power rule, p to the x to the p minus 1. Right? So that power rule in general. Right. Let's see if we can simplify this. Right? So I just write 1 over x never mind, I just want to slow down, rewrite this step. Right. Yeah, that's fine. So we have 1 over x. We can write the bottom as a fraction, right? Like this. And then flip it, multiply reciprocal. Right. Yeah, it's better to write like that. So divide by fraction is multiply reciprocal. The one on top, that go to the bottom. The top here just 1. Right. Now, what we have here is we have x by default is to the first power, and then x to the power p minus 1. When we multiply two things with the same base, we add the exponent, right? We have to adjust something. Right. That p is there, and then we have x to the power of, let's see, 1 plus p minus 1. Because 1 and 1 cancel out, so just x to the p power. Right. Next, let's put in infinity. 1 over p times infinity to the p power. Right. Where p is positive, even though it is like 0.5, that's still equal to square root of infinity, which is still infinity. And obviously, if infinity to the 5 power is still infinity. So bottom line is, doesn't matter. The bottom is 1 over infinity. Now, which is equal to 0, right? But it's not as important. Now that we write 1 over infinity, obviously we can see which one go faster, right? The bottom is bigger than the top, so the bottom go faster to infinity. Yeah. So when we have at the bottom, just write the fraction, and then if the bottom is bigger, meaning the bottom goes to infinity faster. Right. So that's what we have. Right. So let's take a 5-minute break here. We continue at 9:10. that goes to 0, equal to 0, right? Cannot really take attendance with the online setting like this. So I only ask you to just go to the discussion board and then introduce yourself. As long as you do that, it's fine. I realize it's kind of difficult to ask you to sit out and for 3 hours to go through all of this where you can watch later. And at this time, during this time, the last thing I want is I have to force you to do something. Yeah. So as flexible as possible. That's what I try to get here. So that's why I put a video on YouTube, and then also record it. Available the for replay later. I mean, let me answer that on the chat first. Yeah. Actually, since this is lecture, if I want to, I can turn off the recorded option and ask you to be there live. But for 3 hours, that's a bit much. At 8 o'clock, yeah, a little bit much also. So that's why I enable the replay option. Yeah, as much as I want everybody to be here, but during this time, you may have something more important to do at this time. So cut you some slack. Right. Also, I'm not sure if I asked you this before, but did you? Because usually, if it is the campus open, you can go to the library and go to the mass spot. I'm not sure how the mass spot operate during this time. Maybe they have something online. I'm not sure, but I hope you find all the useful resource. I do have office hour first day. I did not set it up yet, but starting this weekend, I will be I'll be on Google Hangout. So if you I'm not sure if usually if I ask I will be on certain time. Nobody gonna. If I ask you to schedule an appointment, nobody could do that. So maybe next week where we have a test. Before that, I will have some certain time, and then I'll be there. If you have any question, just hop in and ask a question, and then you don't have to be there. So before a test next week, I'm going to do that. So let's continue. I'm going to skip the second example here. I'm going to skip that one. Just go straight to here. And to be more clear, that is the power function will grow faster. Yeah, we should write that. Right, 2. In this case, 3. Which one is faster? The power function or the exponential function? Of course, where p is positive. Right. So it doesn't have to be this one divided by that one or that one divided by this one. It doesn't matter. Just take one divided by the others. Let's just do that. Right. And we don't even need to write f of x or g of x. It doesn't matter. I just put two functions, set up a ratio like that. Let's try e to the x over x to the p. Right? Just check the ratio of them. Doesn't matter. One on top, one at the bottom. Right. Now, and x go to infinity. Let's just write this down. Infinity to the e to infinity, and then infinity to the p power. Both of them still infinity over infinity, right? So which is indeterminate. And if it is indeterminate, we can use the Hospital rule. By the way, please remind me to update that. I forgot to update the section. Always at the end, almost at the end. Before I realize this is section 7.6. Sorry. Yeah, if I forgot to do that, please remind me. This is easier for the replayed, so they know exactly what section we're talking about. Right, indeterminate, so we can use the Hospital rule. Derivative of the top, derivative of the bottom. That is the Hospital rule. Right, the exponential function derivative is still that. And then x to the p is px to the p minus 1. Right, and if we use put in infinity in here, we still have infinity over infinity. Right. That makes things a little bit easier to do. Instead of saying p is positive, let's say p is the natural numbers. meaning 1, 2, 3, 4 or so. Right, let's do that. It will be easier to do. Right. Now, of course, that's still infinity over infinity unless p is 1, right? If p is 1, then 1 minus 1 is 0, so that's to 0 power. Regardless, that's still infinity over infinity, meaning we still apply L'Hopital rule. Derivative of e to the x, we still do that. Derivative of the top, derivative of the bottom. Derivative of e to the x, still e to the x. And then derivative of this, we're going to take the power down again. And then we have x to the power p minus 1, minus 1 again, p minus 2. So we can do this repeatedly. The top is still just e to the x as always. Derivative of e to the x, still e to the x. So the top remain e to the x. The bottom we have p times p minus 1. We can do this until 1. So just take the power down. So the power will just decrease every time from p minus 1, p minus 2, and ultimately x to the 0 power, where we take down the 1, x to the 0 power. Now, on the p times p minus 1 on the way to 2 times 1, that is p factorial. And x to 0 power is 1. So ultimately, we will have x goes to infinity, e to the x still on the top, the bottom is p factorial. P factorial, it is a big number, but since p is constant, it is going to be constant. So what we have is e to infinity, when we put in infinity, and p factorial is going to be constant. So we have infinity divided by constant. Doesn't matter how big it is, that constant is. It's not as big as infinity, right? So obviously, infinity is bigger than constant. By the way, the constant is something that we know, so it's not going to be infinity. So when we do that, bigger on the top, so the top is faster. So that is the idea. Just put the ratio of two functions and then find the limit as x go to infinity. At the bottom, whatever bigger on top will go faster. The top will go faster. If the bottom is bigger, then the bottom go faster. Right? So whatever bigger will go faster to infinity. So the concept is pretty simple. There. Next we have this theorem. I just summarize everything. Right. So now we use the notation . That notation means then G goes a lot faster than F. Right. So that meaning grow faster than the other. Right. And I'm just going to write that what we have here in the theorem. And again, this is not 9, that is Q. X to the P, X to the P, ln R to the X. On the coefficient make it a lot more complicated than it actually is. Exponential, super exponential. Right, just like in the note. Let me zoom in. Right. So, in that order, P, Q, R, S are positive and B is bigger than 1. So, P, Q, R, S positive and B bigger than 1. So, by the way, when I put everything in the formula sheet, suddenly this one will be there. So, right now we will just compare the rates. Which one go faster to infinity? But later on, when we go to series, this will be important. Next we'll go to section 6.1. On this section we use the calculator a lot, so I still keep the calculator there. Right, update the section. Right, there you go. By the way, as mentioned before, even though I don't cannot take attendance during this time, but what I can do is at the end of the semester I will ask you to send in some of the notes that you take. Either you watch the replay or you be here live. You should be able to have the note written. Right. Area of regions between curves. Right. So the definition is, I'm sorry, on that side, And so we have two functions pretty much. The graph will be two curves, and we're trying to find the area between them. I'm not going to write exactly as we have there, but just say f of g continuous. Let's assume f of x bigger than or equal to g of x, meaning the function f of x is above the function g of x. Then when we're trying to find the area between so the area between the two graphs, or we say it is bounded by the graph from A to B. So we're going to write the area is equal to, and we're going to say the function above minus the function below. Right. Now let's draw a little sketch on the side. We have the function above, and the function below. And we just assume that f of x is bigger than or equal to g of x. And we want to find the area x equal to a, x equal to b. Right, meaning that we're going to find the area between the two graphs, meaning we're talking about this area here. So obviously the area have to be greater than or equal to 0. Area cannot be negative. So let's write down the note here. First, area cannot be negative. And second, because it cannot be negative, we have to take something bigger function minus the smaller function. So we're going to take, I guess we'll just write this bigger function. Subtract a smaller function. To ensure that it is positive. A bigger number minus a smaller number is going to be positive. So that's why we ensure that it will not be negative. So it was 2. And in this case, the bigger function is the one above. The bigger function here is going to be above. A smaller function is below. Right. So it's pretty straightforward. Right. Let's go to the first example. It says set up the integrals. And next then use the calculator. To evaluate the area, of the region bounded by these two graphs, f of x 4 over square root of x plus 1 and g of x equal x minus 1 and the y-axis. Right, we have the graph in the note, but I want to graph that again on the calculator. Right. By the way, I did send you the link of put in the calculator on the computer, right? And certainly you can use that on the test. Not sure about the final yet, but certainly you can do that on the test. Right. So first, didn't say anything. So we just have to graph those two functions. Okay. First, there's a ratio here, alpha y equal 2, and that gives us a ratio of 4 over square root of x plus 1. Right, so that function. And then the other function is x minus 1, right? Let's see the graph. Right, that's good. If we want to zoom in, we can always hit zoom and then zoom in. But usually I will try to zoom just the windows that I'm interested in. So just zoom box. Find the first one, zoom box. So it's like we want to use with the mouse. So let's say we're trying to blow up this window. So the top left and the bottom right. Right, we're going to blow up this window. Hit enter. Again, zoom, option number 1, zoom box, and then we just select the box that we want to zoom in. Right, so that is the function. Look like this point is 4 and this is 1, and the intersection here is 1, 2, 3, so it's 3. So that's what it look like. So we're trying to sketch on the calculator, on paper, just get the idea of what it look like. Right, so first of all, that function, the top function go 4, and then let's say that like 1, 2, 3, 1, 2, 3, it's gonna be 2, right? Right, so yeah. And then next, x, y go to x minus 1. On the graph, we see the intersection is when x equal to 3. And then so we have f of x and then g of x. And then the y-axis. Right, so what we're trying to find is the area of this region here. Right? So, like I said, it helped to try to get the graph of the using the calculator. And on here we can find the intersection. It's 3. Right. If we don't know to find that, and then we have to make these two equal to, and we solve for it. But if we have a calculator, it is easy to see the intersection at x equal to 3. We're not sure if this is equal to 2 or not. This is not important. We only worry about the x values here. That one is just easy to see what the graph look like. Right. Now, try to find the area of this region. Right. So, it's going to be an integral. The x values, this region go from x equal to 0 to x equal to 3. So that will be the limits. And then just the function that is above, which is bigger, minus the function below, which is smaller. So something bigger minus something smaller. So we ensure that it's going to be positive. The area cannot be negative. So that's why we just say in this case, f of x is bigger. We'll subtract the smaller function. Right. So will be equal to integral from 0 to 3. F of x is 4 over square root of x plus 1 minus x minus 1. Right? Right. And that's where we use the calculator also to evaluate. Is that not difficult? That's not that difficult. We use substitution if we want to do it by hand. Right. So, second mode, too quick. Now, math, and then we go to integral. When you get used to it, that is option 9. Just hit 9. Right. It goes from 0 to 3. And then we have those two functions. Right? I'm going to enter it again, but we don't need to. Alpha y equal, reverse a fraction, 4 over square root of x plus 1. Where's the x? And then minus x minus 1 dx. Right, 6.5 can have a fraction 13 halves. Right. Now, even better, once again, math, option number 9, integral from 0 to 3. Notice we enter this into y1, and we enter that into y2. So all we need is just give them the variable. So we need to have y1. So if you use in this calculator, alpha trace, that is y1, minus alpha trace y2 dx. Also the same thing. Now, if you don't want to enter it like that, you can still go from 0 to 3. And the variable is variable, y variable, function, y1, subtract, variable, y variable, function, y2, Right, still the same thing. We try to give the leave the answer in fraction as possible, because the decimal we're not sure if it is rounding or not. So try to keep as a fraction if it's possible. By the way, I'm just going to change this real quick. If we're using the classic calculator, when we have math number 9, it is in this form. Don't worry, it's still a little bit more work, but we still find the integral of the difference of two functions where the variable is x and x goes from 0 to 3. That's still the same thing, but look different. Whenever possible, if we can have a choice, leave that as the math print, so the answer will look better, and the answer is, the question is easy to put in the calculator. Right, so we have that first example there. Like I said, just trying to get the idea of what the graph look like. The function above minus the function below, the bigger one minus the smaller one. Next. You mean hit math, right? And then we go down and choose the math print. If it's possible, choose the math print. If not, if you cannot go to the second page, then we just have to use hit math number 9 and use the classic one. Sorry, remember I sent you a link so you can install the TI-84 on the computer, and certainly you can use that on the test. Anyway, hit mode and go to math print. Oh, if the answer, I think if on your calculator, yes, the TI-84 will have this option. By the way, if you want to, let's just force the answer in decimal. Let's see what happened. Okay, go up. Oh, no, it does. the TI-84 color, they certainly can do that, but I guess it doesn't work. Yeah. So yes, the TI-84 we do that. The TI-83. Let's see if I can have the TI-83 here. Just a second, I think I have it. Oh, yes. Right. Nope. Yeah, so that is the TI-83. And when we hit math, option number 9, they can only give you this. It's a little bit bigger. Yeah. So we can only see that. sorry. Right, we're back. Yeah. Hi, we're good. Next, find the area bounded by yeah, you're right. The TI-84 we certainly can enter fraction and can give us the math print function. So you have f of x equal to x plus 3 and g of x 2 absolute values of 2x. Right. Now let's put on the graph. Of course, we can graph this by hand, but it will be faster if we use a calculator. We're going to graph it by hand again anyway. Right. Absolute values of x. How do we get absolute values? I think it's in math. Go to numerical, the second tab. ABS. That means absolute values of 2x. Right. Let's see the graph. By the way, on your calculator, it might not look like this. If you want to, hit zoom number 6. Go to the standard zoom. Now it will look like this because earlier we zoomed in the box, right? Now we zoom it back to the standard zoom number 6. So that is the standard windows from -10 to -10, -10 to -10, x and y. Right. So look like we have that kind of a triangle here. Right. Just like the last problem, we're going to zoom in that box. So zoom number 1. Shows upper left corner, right? Hit enter and then go to bottom right corner. So that's good, right? Hit enter. Right. Right. Look like that 1, 2, 3, 4, 5, 6. Right, two functions. First, there's the v. Sorry. First, there's the v. To absolute value of x, it's easy to just I don't zoom number 6. This is the standard, right? If we want to zoom into a box closer to see where are the points, hit zoom. The zoom box is first option, so zoom and then enter. Then we can select the box. To select the box, go to the upper left corner. So it's upper left, hit enter, and then go to the lower right. So just like when you, if you have a mouse, so just select, hold on the top left, and then the bottom right. And when we have the windows, hit enter, it will zoom inside that box only, so it is easier to see, right? So it looks like this 1 and 2, and then this is a V, so kind of run pencil first. That's a V. Next, right. See, there's a pawn here, 3, and then the pawn here, 2. So we have that. By the way, if we want to graph this by hand, it's not that difficult. Just choose some value for x. Just make a table, if you will. Let's see, for this function, when x equal to 0, y equal to 0 plus 3, so it's 3. When x equal to 1, 1 plus 3 is 4. Right. So, yeah. That's easy, right? Now, for this function, x, y equal to absolute values of 2x, 0, absolute values of 2 times 0 is still 0. One, and then if we have negative 1, absolute value of negative 2 is 2. Right, so that's why we have this pawn. Right, anyway, on the graph we see intersection is at negative 1 and all the way to 3. It is easy to see the on the graph, right? There. Right. So we have the graph, absolute values in red. And then we'll talk about this region here. Right. So now if we have a calculator, now we're going to do this by hand, but we're going to set up the integral. The x values, remember the integral is only dx, so we only need to give the x values negative 1 to 3. That's where those intersections are. And then on here, so obviously which one is above, which one is below. We can see that, right? The line is above the v. So here we have f of x and then g of x. The function above minus the function below. Right? Right. So let's see what we did enter. So x plus 3 is y1, absolute value of 2x is y2, right? So math, option number 9, integral that goes from negative 1 to 3. And we have alpha trace bottom menu pop up, y1 minus alpha trace y2, right? Right, we have 6 equal to 6. If we use the calculator, right, now let's do this by hand. Right, the problem with this by hand is, let me just write the problem out. F of x is x plus 3. Subtract absolute values of 2x. Now there's a problem. Remember when we do the integral, again, we have all the derivative and integral rules, and that doesn't include the absolute values, right? So that's the problem. So before we go any further, absolute values of a number means distance from that point to 0, and the distance cannot be negative, so it will be the same number if it is greater than or equal to 0, and it's going to be opposite to that if it is less than 0. So that is the definition of absolute value. Right. Obviously we go from -1 to 3, some of them is going to be positive and some of them is negative, right? Meaning, take a look at this. From -1 to 0, all the x is negative. From 0 to 3, all the x is positive. Right. Now, just do the math first. So we're going to have the integral from -1 to 0, because we have to filter out all the negative values of x. -1 to 0 is negative. Now if it is negative, absolute values is going to be negative. And then we split from 0 to 3. So we filter out all the negative and all the positive, because when it's positive, absolute values is going to be the same. If it's positive, it's going to be the same. So just minus 2x. Right. X negative is opposite. When x positive, it's going to be the same. Right? And because if we look at this graph, that part here is y equal to -2x, and that part here is y equal to 2x. There's a negative here. Right. Now, where does 0 come from? Because there's the absolute values here, I need to have all the positive and all the negative. So from -1 to 3, some of them is negative, some of them is positive. So we have to filter out from -1 to 0, all of those numbers will be negative, right? So from -1 to 0 is negative. And then from 0 to 3, all those numbers will be positive. So when we have absolute values, we have to split the integral so that we have all the positives and then all the negatives. The negatives give us opposite to the absolute, what inside the absolute values, and the positive will stay the same. We have to split the integral where we have absolute values. Yeah. And by the way, the -1 and the 3, I get that from the graph. Intersection is -1 and 3. Right. Now let's simplify this. x minus the negative, so that will be 3x plus 3. And x minus 2x, so that minus x plus 3. We have to do at least one problem by hand, right? Otherwise, yeah, another person watching this may have a problem. That calculation, we don't do anything. We use the calculator for every problem. Right, so integral of x will be x squared over 2 plus 3x. The integral here go from -1 to 0. And then we have -1 x will be x squared over 2 plus 3 going from 0 to 3. So that is 3/2. I'm going to put in 0 first. And then put in -1. Same thing here, put in the 3. I forgot the x here, right? By the way, if you see anything that's not right, just let me know. Sometimes I'm too focused on park and then the other things. So make sure that the stream is good, and then could be distracted somewhere. But so that we put in 3, and then we're going to put in 0. So upper limits, put it in, and the lower limit, put it in and subtract. So standard fundamental theorem of calculus. Right. Now this is easy. That's 0. And what's that? Negative 3/2 -1 to square, so it's positive. So 3/2 minus 3 plus that one also goes to 0. 9 square, so that is 9. 3 square is 9 half plus 9. So what we have is minus 3.5, 3/2 minus that's a plus 3 minus 9/2 plus 9. So that gives us 12, and 3 and 9, that's 12. So 12 minus 12/2, which is 6. 12 minus 6 is 6. Of course, that will be the same as what we have using the calculator. But this one, we just do it by hand. Right. Let's take another 5-minute break. We continue at 10:11. Usually during a break, I will check email if you have anything. Right, nothing. On the test, you can just use your calculator. But I'm not going to ask you all of them, just the answer on the test. On the test, I may ask you to set up the integral, so you might have to write that as the answer. Yeah, sometimes just have to write the integral as the answer. Sometimes I ask you for the end result. Sometimes I just ask you to set up the integral. And at this point, I think setting up the integral is a lot more important than to evaluate it. And I will focus on that mainly. Usually, if it is something that you have to do it by hand, it will be something very simple. Something like this. I'm not going to ask you. Yeah, this one with substitution, and then there will be a lot. It's not that it's impossible to do. It's actually very easy to do. But the focus here is how to set up the integral, because the section is the area between the two curves. So it's not only in calculus 2, in calculus 3, this will be very important. We have to be able to set up the integral, evaluate them. It's not that. It's secondary to how to set it up. To answer to that question, whatever the question asks you, if the question asks for the end result, you can just use the calculator. If it asks you to set up the integral, then we don't need to evaluate it. Right. Go to the second part. Area between the two curves horizontally. That means with respect to y. Right. So, now compared to the definition we have earlier, I'm going to write almost the same, except earlier we have the function in terms of x, now we have the function in terms of y. F and g are continuous. And assume that f is bigger than y. F is bigger than g, sorry. On the interval from C to D. Then the area between now the function the x in terms of y Thanks. Oh, somebody asked where the absolute values. Hit math. Go to the numerical tab. So hit the arrow. And then to the first option. Absolute values. Just hit enter. So that is absolute values. Right. Again, if it is in the classic mode, it will be different. Yeah. Just give us this instead of the math print. So whenever possible, keep the math print. So the absolute values will look better. Right. So math, go to the second tab. The first option is absolute values. Right. So it's pretty much just like what we have earlier, but this time it's going to be a function on the right minus a function on the left. The bigger one minus the smaller one. It is always the bigger minus the smaller. And let's write the note just like we have earlier. Once again, area cannot be negative. And then we just take the bigger function minus the smaller function. This is always like that to ensure it's going to be positive. The bigger function in this case is whatever the function on the right, because the x-axis go like this. The bigger function is on this side and the smaller function is on that side, so it's bigger. Is whatever this, and that is the smaller function. Actually, the graph is much better on that side. So, meaning that when we subtract, the bigger function is on the right and the smaller function is on the left. Right. Let's look at the first example. Find the area bounded. Wait. First one. Scratch that. Find the area. Not in the first quadrant. Just ignore that part. Find the area bounded by y equal to x cubed, y equal to x plus 6, and the x-axis. Right. Of course, we try to graph this too. Right. Y equal to x cubed. That is x cubed. X times x times x. I'll just use x to the power 3. Right. And then x plus 6. Let's see the graph. All right. Certainly we don't see the whole big picture, right? So in that case, zoom out, or usually zoom number 6. That is the standard Windows. So zoom number 6, standard Windows. Should look like, and then of course the x-axis, which is y equal to 0. So we're talking about kind of this region here. So zoom number 1, and we're talking about this region. So up, hit enter. So trying to zoom out, zoom into this box, try to focus on this box. It is a lot better than do the zoom box than to do the zoom in, because zoom in we don't know what we focus on, but this we know exactly what we focus on. X cube and x plus 6, right? So let's see on the x plus 6, 1 2 3 4 5 negative 6, and then 6 up, and then this will be 1 2, right? So on the x-axis at least have to be from negative 6 to 2. Right. Try to draw that very big. Right. From negative 6, 5 4 3 2 1 0, and then 2 on the right. Right. So we have to get that from the graph. But ways is also to do it by hand as well. Let's say we have y equal to x cubed, x equal to 0, y equal to 0, x equal to 1, y equal to 1, x equal to negative 1, negative 1 cubed is negative 1. So negative 1, negative 1, 0, 0, 1 and 1, and then if we put 2 in, it gives us 8. 1 2 3 4 5 6 7 8. Oh, that is enough. Right, use pencil here. And that's why we roll with pencil. Right, so on the test I try to give you the graph, so you don't have to draw it. Right, y equal to x cubed, like that. Next, y equal to x plus 6. This is easy. X equal to 0, 0 plus 6 is 6. X equal to 0, 1 2 3 4 5 6, and x equal to 1, 1 plus 6 7, so 7. So those 2 points. And when x equal to -6, y equal to 0. So we do have that. And then the x-axis here. So obviously we're talking about this region, trying to find the area of this part, right? By the way, the intersection here, I got that from the graph. This is 2. Of course, if we don't know that, we just make the 2 equations equal. So we make them equal. X cubed equal to x plus 6. And we just solve this cubic equation. That's not that bad. Alright, so we have that. Right. Now how to set up this integral. Right. Now, there's 2 options. First, according to the previous part of the section, we can take the function above minus the function below, right? Remember, can always do that. Now, the problem with this region is, what's wrong with this? As you see, for this region, try to focus here. If this is what we have the function, the line above, and then the line below, right? So we're going to take the line minus the horizontal line. So from -6 to 0, the diagonal line above the horizontal line. However, from 0 to 2, the diagonal line above the curve. So there's the inconsistency between the boundaries. Once again, for line, diagonal line to do it. But if we have to do this using dx, it has to be like this. We have to split from -2 to 0. Sorry, from -6 to 0. Because from this region, the function above is x plus 6. The function below is y equal to 0. And then on the other side, the function above is y equal to x plus 6. But the function below is x cubed. We can do this as well. So once again, if there is the inconsistency between the 2 boundaries, we have to split that, because within one integral we have only 2 boundaries. Here above we have 1 boundary, which is okay. The bottom 1 and then 2. That doesn't work. We want 1 above, 1 below. That's why we have to split. So in here consistently from -6 to 0, that above, that below, which is good. Now from 0 to 2, that's 1 above, that's 1 below, which is good. So we can only have 1 boundary for each integral. So that's why if we use dx, it has to be like this. So this is one way to do it, is use that integral. The second one is, now instead of do dx, we use dy. Now on dy in particular, we will look from left to right, right? So I just use the purple here. So horizontally from left to right, what we do have here, the consistency, if we look in this direction from left to right. Of course, this function on the right, that function on the left. When we see that, when we look at horizontally, consistently, the left function is bounded by that curve, that line, and the right boundary is bounded by the curve, right? So the left is bounded by the diagonal line, the right is bounded by the curve. So we have one boundary from the left and one boundary from the right. The function on the right is bigger than the function on the left. Therefore, we're going to use that. However, if we use horizontally, this has to be dy, and the y here is going to be go from 0, and that point will be 8. Why do we know that? Because we have this point 2 and 8. So if we use dy, we write the limit for y 0 to 8, right? Now, the difficult part. What subtract what? Right, we know that this is going to be this one on the left and this curve on the right, right? And we have to get something bigger minus something smaller. The bigger one is the curve, the smaller one is the line. So we have to go with the curve first and with the line. So that function minus that function, the one on the right minus the one on the left, the one that is bigger minus the one that is smaller. So we go with that one minus that. Right, so that's the first thing. Second, this is y, so all the variables have to be in terms of y. Now, if y equal to x cubed, what is going to be x equal to? So to solve for x, we're going to take the cube root on both sides. So cube root of y equal to x. So we have x equal to cube root of y. We have to write the function in terms of y. And that is the function on the right, which is bigger. Right? And the function on the left, again, we have to write that in terms of y. So y is a variable. So if y equal to x plus 6, subtract 6 on the other side, y minus 6 is equal to x. And we're going to use this function instead. Remember, this has to be a function of y. So subtract y minus 6. Right. So that is the integral. Now if we do that, let's see what we have. Math number 9, from 0 to 8. Cube root. Right. No, it go to... Wait, where's the negative infinity come from? Right, you mean the limits. Oh, the limit, this is the y, so we just write 0 to 8. Oh, we do have the x-axis here, right? So we're not going to get below the x-axis. Right. Yeah, thanks. Otherwise, yes, this right, you're right. This region goes indefinitely to negative infinity, but we do have the x-axis. So we're going to stop there. We cut it off right there. So that's why we go from 0 to 8. Right? No. Now we just do that. Integral from 0 to 8. Right. Where's the cube root? I think it's math. Oh, right there. Hit math. Option number 4. Cube root of y. It will be a lot easier just to type x instead of y. So I use x. and then subtract x minus 6 and then x. Ah. 28. Then we say y with the 0.37 here, actually it is 28, but the rounding error, the calculator, when they do the approximation, there's some error, so that's why this one should be just 28. You should not have this problem on the test. Actually, this one is simple enough. Why don't we just do it by hand? Right. So I have 0 to 8 cube root of y, so y to the 1/3 minus y minus a negative, so that's a plus 6. Integral will be y to the 1/3 plus 1. 1 over 3 plus 1 is 4 over 3. 4 over 3 minus y squared over 2 plus 6y. Go from 0 to 8. Divide by 4/3. Multiply reciprocal. 3 over 4. Y to the 4/3 minus divide by 2 is multiplied by 1/2. Right. Going to put 8 in. And we're going to put in 0. Put in 0, all of them is just 0, so we just subtract 0. Right. Just use the calculator there. Usually it will be better. I just stored 8 into x. And I enter 3 over 4 x to the 4/3. So I use x instead of 8. Minus 1/2 or 0.5 times a squared or x squared plus 48. Yeah, should be 28. Right. So that is the region that where we set up using dy, because it is easier. With respect to y, when we look horizontally, one function on the left, one function on the right, which is good. A function on the right minus a function on the left. Now, once again, if we look that up and down with respect to x, if we use dx, above, below, there is inconsistency of the function below. So we have to split in two. By the way, I'm going to put this in the calculator too. We should have 28 as well. Math 9 0. Shoot. Negative 6 to 0 of x plus 6 plus integral from 0 to 2 of x plus 6 minus x cubed dx. Yeah, that should be the same. And then you say, how do you know on the test if you have to use dx or dy? Well, first of all, when we look at the problem, if there is consistency of the limits, one above, one below, or one on the left, one on the right, then we choose dx dy accordingly. Now, some question I will ask you to set both using dx dy and using dx or using dy. So we have to be able to do both. If it is dy, the function has to be in terms of y. If it is dx, obviously the function have to be in terms of x, and the limits, whatever the limits are for x and for y, depends on the problem. Right, so we have that. Alright, just like the next example, we're going to set using both dx and dy. So pretty much just like this one. C. Example 2. Find the area of the region in the first quadrant bounded by these two functions, y equal to x to the 2 over 3 and y equal to x minus 4. Notice that this is in the first quadrant, so x and y must be positive. Right, I will graph that as well. Y equal to x to the 2/3 and then y equal to x minus 4. We have to change the windows though. It's only in the first quadrant. Right, we don't see anything. We see those two graphs but no intersection whatsoever. So zoom number 6, hit zoom and then number 6. Now that gives us the standard windows. Look like, by the way, this is only on the first quadrant, so we have to cut off here and there. That is the region we're talking about. Right? So let's zoom in the first quadrant. Zoom box. So zoom and then number 1. Right. Move to the upper left corner. That's fine. And then the lower right. Remember, it's only on the first quadrant. We do not go. It's only in the first quadrant, so we don't have to go to this point. Right? Right. Okay. That point, it is about here. Right? So that point, right? So 1, 2, 3, 4, 5, 6, 7, 8. Never mind, let me do that again. Zoom box. a little bit further down. Right, that's box big enough. Right, so we have that. So that intersection here, let's see, 1 2 3 4 5 6 7 and 8. Looks like 8. By the way, can we turn the grid on? Second format. Oh yeah, why don't we turn the grid on? So second zoom, turn the grid on. Much better. I forgot about this. Oh, 0 and 8. From previous prompt or from this prompt, both of them have 0 to 8. Alright. Anyway, on the last prompt, the reason we get 8 because when x equal to 2, y equal to 8, and when x equal to 2, y equal to 8. So we do have the intersection on both of them. That's from the previous prompt. This prompt is going to be the same. When x equal to, this is 8, and then y will be 1 2 3 4. So this point here is 4 and 8. Yeah, again, it will be much better if we hit second format and turn the grid on. So in that case, we see the point will snap into place, easy to see. Right, so that point up there is 4 and 8. Right, so we have them as far as 8 on the right, and up has to be at least 4. Because this is only on the first quadrant, so x and y have to be greater than 0. So right, now let's look at y equal to x to the 2/3 first. We can always choose some values for x and for y. When x equal to 0, obviously 0 to the 0 power, 0 to the 2/3 is 0. 1 raised to any power is still 1. And according to the graph, is 8 to the 2/3. What is that? 8 to the 2/3 is 4. Right. So I have to point 8 and 4. 2, 4, 6, 8, 2, 4. So that point. Right. So I have this. And then on the other side too. We wouldn't worry about that. Worry on the first quadrant. X and Y positive. Right. So that's the first graph. The first function. The second function, linear function. This should be easy. X equal to 0. It's going to be -4. That doesn't help at all. It's way down here. To choose something bigger than like 4. 4 minus 4 is 0. Yep, so that's good. And then x equal to 5. 5 minus 4 is 1. So And if we go to when x equal to 8, 8 minus 4 is 4. So in this we have the intersection of 8 and 4. This time problem, it will be useful if we use we have the calculator to see what the graph look like. Okay, so this is y equal to x minus 4, and then above that y is there a lag? Look like I got some frame dropped. It should be okay now. Right. So on this one we have to do both dx and then dy. So first it's going to be dx, and then it will be dy. Now, by the way, this is in the first quadrant, so we're not worried about the part below here. Right, so this is the region we're trying to find the area. Right, now I'll ask you, what is the function above? That's easy, that curve, right? Now, what is the function below? Now that's not easy. Below we see two functions. One is this diagonal line, and one is this horizontal line. Right? So that's the bad thing here. If we use dx, then it's going to be from the function above minus the function below. Remember, if dx, I'm just going to write in general, is something above minus something below. In general, the one above here is the curve, which is good. The bottom though, there are two of them. That doesn't work. So in order to make it work, we have to split in two. And we know this point is 4, right? X equal to 4, y equal to 0. So we have to split in two. First, we go from 0 to 4. In that case, the function above is x to the 2/3. dx, so we write the function of x. And the function below is the x-axis, or y equal to 0. Right, so that part. Right? Consistently, the line, the curve above the horizontal line. Now, we shift gear to here. From 4 to 8, because the intersection is at when x equal to 8. When 4 to 8, the function above is the curve. Right? The function above minus the function below, which is x minus 4. Right. So if we're using dx, where we use the function above minus the function below, we have to split because there are two functions at the bottom, two functions are below. So we have to split. So the boundary will be consistent. curve horizontal line, the curve diagonal line. So that's what we have here. So that is if we use dx. Now if we use dy, I think after this one we done for the day. If we're going to use dy, we're going to use the function on the right minus the function on the left. On the right minus the left, something bigger minus something smaller. It's always like that, right? So if we look at this function on the right, function on the right minus the function on the left. In particular, if we go that direction, this is on the right, that is on the left. And good thing here is there's only one boundary from the left and one boundary from the right. So one boundary on each side. So we need only one integral. So we don't need two like this. Only need one. And this is going to be dy. And the y values from here, the regions between y equal to 0 to y equal to 80. Sorry, 4. Yeah, y from 0 to 4. So that is the limit for y. Now we just need to say the function on the right minus the function on the left. The function on the right is x minus 4, y equal to x minus 4. However, we're not going to use that because it is y. It has to be the function in terms of y. So if y is equal to x minus 4, y done with plus 4 on both sides, and we have x equal to y plus 4. That is the function on the right in terms of y. And y to x to the 2/3. What we do here is, I'm going back to this in a minute. Y equal to x to the 2/3. I'm going to raise both sides to the 3/2 power. Power times power. Power times power. 2/3 times 3/2 is 1. And y to the 3/2. So equivalently, y equal to x to the 2/3 is equivalent to x equal to y to the reciprocal power 3/2. So the function above, a function on the right bigger is y plus 4. The function on the left smaller is y equal to 3/2. Y plus 4 is on the right. And y to the 3/2 on the left. So if we only have one boundary from the left, one boundary from the right, we only need one boundary, or we need to only one integral. If we have more than one boundary on one side, we're going to have more than one integrals. So we have to split. Essentially, this part is very important when we set up the integral. So that's why I go extremely slow here and with a lot of details. But bottom line is, if we use dx, it's going to be above minus below. If it's going to be dy, it will be the right minus the left. Something bigger minus something smaller to ensure the area is positive. By the way, you can put both of them in a calculator. You should get the same thing. Alright. So I think we will stop here. And then we pick it up on Friday. Thank you for being here. Have a nice day. And see you on Friday. I'm going to end the stream here.